Well, thank you for coming tonight, everybody. So tonight I'm going to talk to you about the geology of the Buckeye State, or Ohio geology. And of course, most people, when you say geology, their eyes kind of glaze over. They remember back being a kid and the monotone voice and the boring stuff you had to memorize that didn't mean hardly anything. Hopefully it's not going to be like that, because geology is actually a fascinating topic, and I really wish they would teach it better, because I actually do a lot of history. I do shipwrecks, I do a lot of stuff like that. And to me, geology is just history. It's just really old history. And I think after today, you're going to get a better appreciation for Ohio history in those ancient times. So, first of all, let's look at Ohio. Now, when most people think of Ohio, this is probably what pops into their heads. This is, of course, a Rand McNally road map of Ohio, and this is what people think of. They see cities, connecting roads, maybe Lake Erie, the Ohio River, and every now and then some nice green spots where there's national forests or parks or things like that. Nice, but that's not what pops to my mind when I think of Ohio. When I think of Ohio, this is what pops into my head. This is essentially the bedrock of Ohio overlaid with the topography of Ohio. And this, to me, is really Ohio. Yes, you can put the towns and roads and things in there too, but that's not the interesting part. The interesting part is what's under our feet. And hopefully by the end of tonight, you will have a better appreciation and maybe think of this a little bit more than your typical road map of Ohio. So let's get started. First, I'm going to show you a simpler view of that one. This is just the bedrock that underlays Ohio. All of the bedrock in Ohio is of the Paleozoic Era. Now, I know that means absolutely nothing to most people here, but in the next few slides, I think it'll actually mean a lot. And I think you'll understand better why that is actually incredible. Paleozoic Era, we'll get into it. The other thing, too, is it's really easy to understand Ohio geology. It's not a muddle. It's actually very organized. Pretty much the oldest rock is all over in the western side of the state. And it's about 500 million years old, or as I like to call it, 500 million years old. It's a better way of looking at it. We're talking really old. And then our youngest rock is in the eastern part of the state. 250 million years old, 250 million years old. So that means that as you travel from west to east across the state, you're going from the oldest rock to the youngest rock. Pretty simple, right? And this rock composes all six geologic periods. It's not all six of the Paleozoic. And that's, by the way, actually a pretty incredible thing too. And again, probably doesn't mean much, but it will. And you may ask, why is that the case? Why is that arranged that way? And it just happens because we're tilted underneath. The bedrock is actually tilted up. This is called the Cincinnati Arch. It's a big dome. And all of the old rock comes to the surface there. And then all the younger rock that would be on top of it is now tilted to the east and then sheared off flat. And that's why you get the youngest rock over here in the east and the oldest rock over here in the west. It's just essentially a big dome cut off flat at the top. And that makes it actually pretty easy. So nothing to it, pretty easy. If you find yourself in part of the state, you can instantly say how old that rock is, pretty much, just without even looking at it. Okay, so everybody here, I think, has seen this at some point or another. This is the geologic time scale. You probably saw it in school briefly. And this is kind of the first thing you see when you get taught geology. But they don't really tell you much about it other than, well, here's all of the geologic history of Earth. First of all, the geologic history of Earth, for most part, at least when you do most schools and classes, starts about 570 million years ago. Of course, the Earth is 4.6 billion years old. And so 90% of the history is in this little tiny thing at the bottom. The reason for that is that we can't say a whole lot about it. Partly because the Earth has recycled a good portion of those rocks, but more importantly because pretty much through this entire history, it was all single-cell life. And by the way, life appeared on this planet within the first few 100 million years, maybe 500 million years of its existence. Life just appeared. It happened quick. But it stayed single cell for most of Earth's history. And then around 570 years ago, something called the Cambrian explosion happened. suddenly multicellular life appeared on the landscape. Oxygen became prevalent in the atmosphere. We used to not have oxygen. It used to be a nitrogen, CO2 atmosphere. And so geologists don't talk a lot about the Precambrian because there's not a lot of details. They actually have been learning a lot more in the recent years. Now they can do chemical analysis and all sorts of things, but that's usually an advanced topic. For the most part, we talk about only the last 570 million years of the planet for geologic history. It's not to say that that's boring. That's actually the most interesting part, and that's why geology is always classically focused on that. Now, all of this first part right here is called the Paleozoic, which just means ancient life. Remember I said that Ohio encompasses the Paleozoic? Well, that's what the Paleozoic is. I'll point out the Mesozoic came later. That's the middle life. And the Cenozoic at the top is where we are today, and that's modern life, new life. So Ohio geology actually starts right here. We missed the Cambrian, but it actually starts 500 million years ago, right at the start of the Ordovician. And it goes all the way up to the end of the Permian, about 250 million years ago. So what that means is all of Ohio geology is almost the entire Paleozoic. We missed the Cambrian, too bad. But we actually got all of these geologic periods of the Paleozoic. So why is that cool? Well, first of all, let's say what Ohio geology is not. So Ohio geology is not dinosaurs. I hate to tell you, there's no dinosaurs. The first dinosaurs didn't come in existence until 230 million years ago, right at the start of the Triassic. And by the way, mammals appeared right around the same time. A lot of people think mammals came later than dinosaurs. No, actually both appeared on the landscape pretty much at the same time. For whatever reason, dinosaurs at the end of the Triassic took off and mammals did not. And dinosaurs ruled pretty much the entire Mesozoic, at least the latter part. Through the Jurassic and the Cretaceous, that's the age of dinosaurs. Unfortunately, that's not Ohio geology. Because, well, if you were to find a dinosaur fossil in Ohio, it means one of three things. Either you misidentified it and it's not a dinosaur. Two, it came from somewhere else. Or somebody's just flat out lying that they dug one up. Maybe they found a chicken bone in the backyard. Because, by the way, chickens are dinosaurs. So it kind of counts, I guess. But Ohio, unfortunately, is not dinosaurs. But that's actually a good thing because everybody does dinosaurs. Ohio does some cooler things, I think. So why is this not here anymore? Well, there's a couple of reasons. One, it may have been laid down and then just got eroded away over the eons. We had these pesky things called glaciers. They could have taken most of that sediment away. Two, we actually were not really good sediment preservers for the Mesozoic and Cenozoic. For the most part, a lot of deposits may not have been put down or didn't stay very long, quickly eroded away. Whatever the case, we just don't have from here on up. But that's not to say we don't have really interesting stuff. So right now, the dinosaurs are 67 million years away from us, not including birds. They're still out there. But 67 million years ago, that asteroid came by, whacked them, they were gone, at least the non-avian. The dinosaurs start is anywhere from, depending on where you are in Ohio geology, 50 to 300 million years away from the dinosaurs starting. That means that Ohio geology is further from the dinosaurs than we are today from the dinosaurs. That means that this stuff is, in fact, really, really, really old rock. The dinosaurs are a future, far future memory or thing that's going to happen for when this rock was laid down in Ohio, compared to now looking back at the age of dinosaurs. So let's get started. Let's go to the earliest one, the Ordovician, down here in the southwestern corner of the state. 500 to 440 million years ago, and this is what the world looked like then. Now, you all know about plate tectonics, right? That things move around. I don't think it's very clear to people how much things move around. 500 million years ago, can you find Ohio? Well, what would become Ohio? Here we are, down there. First of all, you'll notice we're south of the equator by about 20 degrees in a warm tropical sea. And we're part of a continent called Laurentia that would eventually become North America. But at the time, didn't look anything like us. And in fact, we were underwater here. We've got the Iapetus Sea. You can see Baltica. That's what would eventually become the Baltic states. Sweden, Norway, Finland, things like that. And down here you've got a series of islands, Avalonia. That would become New England, Nova Scotia, parts of southern England. And up here you got Siberia. And then over here we have Gondwana, huge continent. Kind of dominates the globe, in fact. Most of the land masses are all crammed together in there. Very, very different from today. So let's zoom in. Here's what our part of the world looked like in the Ordovician. There's Ohio right there in a shallow, warm, tropical sea. And because it's a tropical sea, there's corals and, of course, little critters living in the water called diatoms and things that create little calcium shells, and when they die, they drift to the bottom, and they create limestone. And that's why you see limestone in the western part of the state. If you've ever driven along the road cuts here, you see this whitish gray rock, kind of flaky, usually in layers. That's limestone, classic limestone. And it's either from coral reefs or it's from just these little critters dying, floating to the bottom and creating a lime mud that when buried and compressed turns into limestone. And this is what the seas would have looked like. Very different from what you see in the seas today. In fact, one thing I'll point out right now is you don't see a picture of land. Why? Because when Ordovician rock was laid down, there was no life on land at all. No plants, no animals, nothing. It was a barren landscape. That's how old the Ordovician rocks are. No life on land. All life was in the sea. And you can see things in the background. These are called sea lilies or crinoids. You can see these big squid things here called cephalopods. They look sort of like squid or octopus, but different. They have these long, sharp, tapered shells on them. They're relatives of what would become octopus and squid, but they're different. They're cephalopods. The fish look strange, don't they? These are actually fish with no internal skeleton. They have a cartilage skeleton like sharks do, and they don't have jaws. Gill plates haven't evolved yet. And any bone on them is actually bony plates on the outside. They're placoderms, armored fish. Tiny, most tiny, some a little bigger, all jawless, no jaws at all. Very, very weird. Down here at the bottom, you can see some brachiopods. They're like clams, related but different. They're not bivalves. They're brachiopods, a whole different family. And then something that does look familiar. I think most people, how many people have actually seen trilobites? Everybody knows about trilobites. This is the time period when trilobites ruled the earth. They were kind of the dominant thing. This is the most common thing other than corals and things like that. Trilobites and brachiopods are everywhere. And these crinoids too. Let's start with the trilobites because they're really cool. I love trilobites and I so wish they were alive today. Closest you're going to be able to see a trilobite today would be a horseshoe crab, kind of a distant relative. And that's why you always see them kind of painted that way because we think that's what they probably look like. Kind of big eyes, little feet, lots of segments, these big shields and spikes on them and things like that, probably for defense. And they fossilize everywhere. Ohio is filled with trilobite fossils. You can see them here. They all just died in the mud, maybe in a little landslide or something like that. Maybe a mass burial, mass death, something of that nature. But here they are, cute little critters, all preserved from 500 million years ago. And the most common one here in Ohio is a little guy called Flexicalamin. They're not big, the size of a quarter maybe. And usually you find them looking like this, all rolled up in a ball. You know how pill bugs roll up in a ball to defend themselves? These little guys did the same thing. And that's usually how they died. And so most of the time these little fossils are all curled up into a little ball and their death pose is their little defensive position that they ended up dying in. But they're everywhere. And they're kind of cute, I think. They're not big, but they're very cute little guys. But Ohio also has the largest trilobites ever seen. This is Isotellus maximus. The biggest one found, 2 feet long. That's a big trilobite. Most trilobites are usually 4 or 5 inches, 2, 3 inches. This guy's a monster. And it was first discovered and described in Ohio in 1838. One of our first trilobites actually discovered and examined happened to be the biggest trilobite in existence known today. It wasn't until 1985, though, that it became our state invertebrate fossil through a school child's write-in program. A little girl in a school decided it should become the state fossil, the invertebrate fossil. She started a letter writing program. Her classmates did. Pretty soon other schools were doing it. And in 1985, it was finally designated our state invertebrate fossil. So Isotellus maximus here is now our official invertebrate fossil. This is another one, small one, only 8.5 inches long, but boy, I'd love to have this one. This is a really cool fossil. And you can see the little horns on them and things like that. And I definitely can see a horseshoe crab in this guy. Brachiopods, one of the most common fossils you'll find everywhere. They tend to bury themselves in mud, easy for preservation that way. It looks like a clam. It's distantly related to a clam, but a really different family. Clams are bivalves. That means the hinge is actually on the side, and they tend to be symmetrical from top to bottom along the horizontal cut. Whereas brachiopods, the hinge is in the back of the animal, the business end, the mouth is all up front, and they tend not to be very symmetrical from the horizontal cut top to bottom. So most people say, oh look, clam fossils. Well, really they're brachiopods, but close enough. How about this? Anybody know what this is? If you found these, would you know what you were looking at, other than lost pieces of necklace? Lifesavers. Lifesavers, yes, there you go. Lost ancient lifesavers. It's actually really tough. These are actually really common. If you go to any stream in like Lodi, the little public park there, you will see these things everywhere. The clue is these little stalk segments. They're crinoids. Remember those sea lilies in the background? It's the column here, the stalk. It's just the little segments, the columnar segments. They tended to, when they died, break apart into little pieces, and that's how they mostly preserved. It's rare to actually find one intact. They have a little holdfast down here, a stalk. Up here is the mouth, and these feathery arms on the crown that would sit there and filter stuff out and feed the mouth. And by the way, this is an animal. This is not a plant. It looks like a plant, but like most things underwater, things that look like plants are usually animals, and this is no exception. And you can actually still find these guys alive today. You have to get in a submarine, thousands of foot of water, miles deep water, but here's an ancient animal from 500 million years ago. There's its holdfast, the stalk going up to the feathery crown, and he sits there on the bottom just slowly feeding himself with whatever drifts by. I'm a scuba diver, and unfortunately I can't go to those depths, but I can see one of the ancient relatives, a little modified. This is a feather star. It's actually a crinoid. The only thing it's missing is the stalk. Modern crinoids typically don't have that stalk. They still have the holdfast. They sit on top of reefs at night. You always see them on night dives. And their little feather arms are out, and they're actually feeding themselves. If you take your flashlight, you track little shrimp and things, and they get stuck in the arms, and you start to see the arms moving, and it's really very cool. So it's really fun on night dives to play with these. During the end of the night, they actually just literally walk back into little nooks and crannies, fold themselves up and hide during the day. At night, they come out to feed and find high points on the reef and start feeding. So most divers don't even know they're looking at an ancient animal with a very long lineage. Here's another cool fossil from that time period. This doesn't look like much, but this is actually the top predator of the day. This is cephalopod, that octopus squid relative. And of course, in life, they look like this. They actually got really big. Some were up to 5 to 10 foot long. They were big top predators. These guys were pretty much ruled the roost. This was what you feared if you lived in those seas at the time. These cephalopods were kind of what you didn't want to get near. And I'm sure why trilobites had all that armor too. And we can kind of find them today. Towards the end of the Ordovician, you start to see the shells, those long conical shells, start to curl. And they start to look like this. And what does that look like? The nautilus, yes. The nautilus today is the last surviving example of the cephalopod. You've probably heard the nautilus is an ancient animal, the last of its kind. This is what they mean. This is the last cephalopod in its near original form, minus the straight shell, but still pretty close. Okay, so that's the Ordovician, ancient times. Very different ocean than what we would find today. Let's go on to the Silurian now. Silurian, 400 to 440 million years ago. Still a long way ago. And here's what the Earth looked like then. Now, you can see Laurentia has changed a little bit. It's kind of moving, and Gondwana is moving a little bit. Things are getting closer here. And in fact, Avalonia and Baltica have now started to collide with Laurentia, creating mountains. And we are still south of the equator, and we're still in a tropical sea. If we zoom in, here's kind of our part of the world. Ohio is right here, and you'll notice something interesting. We're kind of still in a shallow sea, but we're partly landlocked as well. And in fact, what happened is when there was water here, we had limestone. Sometimes it would get cut off and all of this would evaporate away. And what's left behind? Salt. And so you get salt deposits. And then it would reflood and you get limestone, dry out, salt again. And do you want to guess where all those salt deposits are that are 2,000 feet beneath our feet right now? They're Silurian. This is that time period. The mines under Cleveland and Ashtabula are mining those giant lakes that would periodically flood from the sea, then dry up, flood from the sea and dry up. Every one of those lines on the wall is one of those events. Sort of like the Mediterranean getting blocked, drying up, which it did once, by the way, and then refloods, and then dries up, and then refloods, and dries up. And that's where the salt we mine today comes from. Now, here, the Silurian's 2,000 feet down, but if you go west, it's exposed. Of course, salt kind of dissolves away, but you got plenty of limestone from the Silurian to the west. And that's why we have all of this stuff here we call karst. Karst is just the fancy geology word for limestone. It's important because if you like caves, that's where you're going to find caves. Limestone and caves go together. Rainwater creates carbonic acid, which then dissolves the limestone, and that's how you get caves. And so all of the commercial caves, Cleveland or Ohio caverns, Seneca caverns, Laurel caverns, all of those stuff, the little caves up in Put-in Bay too, are all from this karst deposit, mostly from the Silurian. And that's why you'll only find caves in the western part of the state. You won't find them over in the eastern part of the state. And this is what the seas look like in the Silurian. A little different now. Plants are finally coming ashore. The land is no longer barren. The very first colonizers of land have made it out, and very soon after the plants came insects. Actually, what they were is they were relatives of these guys, the sea scorpions, which did exist a little bit in the Ordovician, but they really took off in the Silurian. And these guys became the top predators. And these guys also got 5 to 10 feet long. Again, I would not want to meet one of these guys. Pretty ferocious looking, and they were something to be feared, I'm sure. They definitely hurt if they bit you. But of course, there's other things too. You can see the fish now look different. They're not the same fish that we see today, but they're definitely getting closer. They're still placoderms, they're still armored fish, but they got jaws now and gill plates. They're starting to look like fish that we think of today. They still don't have the internal bony skeleton, which is bony fish, that's what they're called. But they're on their way. They're getting closer. And the Silurian is called Age of Corals, because corals really took off too. Huge coral reefs, things all over the place, and a lot of limestone from those coral reefs. Here's some of that coral. Probably the most common coral fossil you're going to find in Ohio. It's very distinctive. It's called horn coral. I'll let you guess as to why. And just like modern day coral, it's an animal, not a plant. And it does a little filter feeding. They may or may not have algae in them, just like modern corals that also do photosynthesis. Most corals actually get their food from 2 places, from filtering and from photosynthesis with a symbiotic relationship with internal algae, little critters that live inside them. The horn corals, best we can tell, probably attached to the muddy bottom, kind of bedded themselves in and filtered and lived their lives like that. And that's probably why they're so most common, because they're in mud. So they get buried easily and preserved easily. Fossils are kind of a chancing thing. It doesn't happen often. And all the conditions have to be right. If you live in mud, it's going to be more likely you'll get preserved than if you don't live in mud. And I think that's why horn corals are so common. Now here's something I think most people would see and not even recognize as a fossil. They look right past it. Do you guys see it? These little pieces here on the thing. Here, I'll take away the rock. This is what these look like. They're called bryozoans. And bryozoans are actually really cool animals. Again, these are animals, not plants. Plants don't really seem to be that big of a thing in the ocean. Most of the fossils are animals, even though they look like plants. This is what they would have looked like in life. All sorts of types. You can see feathery types. You can see stalk types. They've gone to great descriptions. There are dozens and dozens and dozens of species, but they're really animals. And the cool thing is it's not one animal. It's hundreds, thousands, millions, maybe even billions of animals to create one unit that looks like a single organism. It's called a colony animal. Sponges are like this. Sponges are actually billions of little animals, all identical, living in something that looks like a larger organism, specializing in various things. Partly, some are drawing in water, Some are sweeping food, some act as photosensors, some expel waste. They all have a different thing. They're acting like a single organism, even though they're all individuals. Very, very cool, and kind of probably the intermediate between single cell and multicellular life. Colony animals kind of are that bridge. Eventually they did become one. But all of them would have had a little gut, little tentacles, mouth, the whole bit. They were all little animals, but they ended up creating things like this, and they still exist today. Ocean divers will see this. These are called soft corals, but they're really bryozoan colonies. How many people have been to a creek, a stream, stagnant body in a pond, a lake, marina, and seen a big gooey ball floating around? It's actually pretty common. Go look next time you're in a pond. Look for a big gooey ball. That's a bryozoan colony, freshwater, and pretty common here in Ohio. You see them all the time, usually in the corner of a marina that everything's kind of stagnant at, or corner of a pond where there isn't much flowing water. But you can actually see these guys today. All right, now we're going to get to the Devonian. Yeah, and Devonian is, by the way, what Cleveland sits on. So right beneath our feet is a lot of Devonian deposits. 400 to 360 million years ago, and this is what the world looked like. Laurentia is gone now. Collisions have happened. A new continent is formed called Euro-America, which you might guess it's a combination of Europe and North America. And Gondwana is getting scarily close. We're still south of the equator, right here, still warm tropical sea, and things are moving. If we zoom in, we're kind of back, still in the ocean, but now we're beginning to become a stagnant sea. These mountains right here are kind of the prototypical Appalachian Mountains. This is from the collisions of Laurentia, Baltica, and now starting collision with Gondwana, which, by the way, that's Africa right there. All of this is pushing up the Appalachians, forming a wall here. We've got mountains that no longer exist in northern Canada, and all of this stuff kind of flows out into this little sea from the east and from the north, and we're about 100 miles offshore in deep, about 300 to 400 foot water, and we're kind of a stagnant sea. In fact, we know the bottom was typically anaerobic, no oxygen, no life either, unless you're an anaerobic bacteria. And we know that because of the world famous Cleveland Shale. Now, how many people have been to Fort Hill and Rocky River Reservation? This is Fort Hill. This is one of the Cleveland Metro Parks, very famous place. It actually has some Indian stuff at that tip up there. But here they are looking for Devonian age fossils sometime in the probably early 1900s. And all of this black shale, it's black because it's anaerobic. Shale that's laid down in oxygen conditions tends to be a grayish color. This is a jet black color, 300 to 400 foot. The surface waters, however, were alive, oxygenated. All sorts of creatures lived there, and when they died, they floated to the bottom and were perfectly preserved. Nothing ate them or scavenged them, and this nice, fine silt preserved them very, very nicely. Plus, things are drifting offshore. There's plants and all sorts of things drifting out into the ocean for 100 miles, 1,500 miles, eventually get waterlogged, sink to the bottom. And so we're actually preserving things from land as well. And this is what Cleveland Shale is famous for. Dunkleosteus, a frightening fish. He's a placoderm, another one of those armored fish, but he's grown to frightening lengths. They think up to 25 foot long. Take a look at that big armored head with those shearing jaws, and they did exactly what you think. They ate pretty much anything they could get in their mouths, including each other, they've discovered. The Cleveland Museum of Natural History started to notice little scars, fresh scars on the head shields that could have only been made by another arthrodire. Means they were eating each other, probably while they were alive, trying to catch and eat the other one. So these were truly frightening fish. And that's why they call the Devonian the age of fishes. Fish life really dominates the sea. This is the top predator now. This is what's going on in the oceans. And it's not just these guys, not just the big armored fish. And there was a bunch of species, not just Dunkleosteus. But these, sharks. Sharks are actually everywhere. They're a nice early species of sharks. It kind of looks like a shark, but a little different. This is Cladoslac, about 2 foot long. And Cleveland Shale, I think, is more famous for this than Dunkleosteus. Yes, everybody loves Dunk. But this is really cool. For reasons unknown, these sharks preserve really well in Cleveland Shale. Usually when you get a shark skeleton, all you get is teeth. You don't get anything else. It's a cartilage fish. You don't know anything about the biology, the fins, nothing. These guys preserve perfectly. Fins, tail, internal organs, even the stomach contents of their last meal are visible in these things. That is very, very, very cool. Kind of unique. You don't get many shark fossils. Cleveland is one of those few places in its Devonian shale deposits where you can find a perfectly fossilized shark. And that's right. And by the way, you'll notice how hard it is to get to these things. Anybody who's tried to climb up shale knows it's crumbly, and you better just not do it. You're going to fall and hurt yourself. These guys would have to come down on ropes and try to get a concretion out and hope there's a fossil in it. This guy, by the way, went to all that work, and it was just one little tiny bone in the concretion. Couldn't even identify it. All for naught. Okay, now let's move on to the Mississippian. For you geologists, connoisseurs out there, I know that the Mississippian and Pennsylvania have been combined into the Carboniferous to be in sync with the rest of the world, but we like doing things differently, and we're going to call it the Mississippian period, even though it's technically the sub-period now, all kind of under the Carboniferous. And this is what the world looked like. Things are now beginning to combine. We're really, really close. Gondwana has moved south of us. Euro-America is right to the north. Ohio is pretty much where it's been for a while now. And collision is beginning with Africa. And that means that our part of the world is getting more mountainous to the east. So here we are again, kind of a coastal is what I would call it. And we varied between land and sea going back and forth, which means we got a lot of sandstone because of all of these mountains, the Appalachian to the north, as well as these mountains up here, all of this is draining out into Ohio. And at times we're just offshore by tens of miles, maybe a mile or two. Sometimes we're right on the shoreline. Sometimes we're even inland a little bit in a river estuary system. And the end result is sandstone. In fact, it's a quartzite sand, quartz from mountain building, metamorphic rock. All of this is getting ground up and washed into our sediments that are what ultimately becomes Ohio. This is what Ohio would have looked like in certain parts. Big sand deltas, massive rivers running off. To our east, it's called the Catskill Delta. That's the Appalachian Mountains. To the north, we're getting stuff from the Canadian Shield. And it's all washing down pure quartz sand into Ohio. And for how many people have been to Berea? World famous Berea sandstone. That's the result. It's all very nice quartzite sand from the upper Devonian, lower Mississippian. They keep going back and forth. By the way, geology constantly changes its mind. Depending on which textbook you pick up at what time, Berea is either very late Devonian or it's very early Mississippian. And they just changed their minds yet again. So who knows? But it's right on the border. So we'll call it Mississippian. This is obviously a little bit offshore because heavy things fall out first and lighter things get further. The shale, fine silt, got the furthest. That's when we're hundreds of miles offshore. Tens of miles offshore, you start to get sand. And if you're right on shore, or maybe even a little inland, you get this thing called Sharon conglomerate. And anybody that's been around Nelson Kennedy ledges and various other places, especially on the east side, you see all of this quartz cobble and this nice sand matrix. Same stuff that's pretty much Berea sandstone, but at the same time, you're getting heavy big stuff now, which means it's still in a river form. It hasn't really gone offshore yet. And so the end result is you're getting these big pebbles that fall out, sometimes 1 or 2 foot thick. And that's probably all one catastrophic event, one big flood event will put down that entire layer. And then you get a little cross bedding, it gets cut by the next flood. And the end result is you end up with this conglomerate. And of course, I've actually been hiking in the woods, and sometimes, a piece breaks off and it looks like this. It looks like concrete. And I've heard people say, oh, somebody poured concrete and left it here in the middle of the forest. Well, nature did that about 300 million years ago. And this is all river-rounded cobble in a sand matrix. You hear one you can see actually broke out loose. And that used to be a big flowing river at one time. Another really cool thing's happening at this time. Land animals are finally coming ashore. Cleveland Geology is laid down right in the middle of the state when land animals come ashore, finally. And this is the relative of all of us. This is a tetrapod. The earliest ones are about 350 million years ago, but they keep making new discoveries and pushing that date back a little bit. And this guy is the ancestor of dinosaurs, birds, mammals, reptiles, amphibians, anything that walks today. This is the relative. There was a bunch of different species. Unfortunately, Ohio doesn't have good preservation. Those sand deltas were not a good preserving environment for fossils. But Pennsylvania, just to our east, has some really cool tetrapod fossils. And believe it or not, Greenland is the next hot place to find tetrapod fossils. They apparently were a good preservation environment back in the day. Unfortunately, here in Ohio, we just have very fragmented marine fossils when you do find them, which is really rare in the Pennsylvanian type deposits. By the way, fun fact. So you ever wonder why we have 5 fingers, 5 toes? Everything has it. Dinosaurs had 5 fingers, 5 toes. Reptiles have 5 fingers, 5 toes. Amphibians have 5 fingers, 5 toes. Birds have 5 fingers, 5 toes. One's pulled up in the dew claw. But everything has 5 fingers, 5 toes. It's due to this guy. Some of the tetrapods had 8 fingers. Some had 12. And some had 5. You want to take a guess who our relative is? Pennsylvanian, the next one. 320 to 290 million years ago. Now we're getting to the eastern part of the state. Now the world looks like this. The collision is fully over. We're now one supercontinent called Pangaea. All of the world's land masses are combined pretty much into one monstrous continent, supercontinent. Everybody's combined into one. There's still a little bit of seas and things around, but for the most part, everybody is together. And Ohio now is right there, moving toward the equator. We're actually going north. And in our part of the world, this is what it looks like. And we are now pretty much a coastal environment, barely in the water, just kind of right on the edge. And this is the time of those great coal swamps, big fern forests. And of course, what do you get? Coal, because it's a coal swamp, right? Oops, I'm sorry. This is what Ohio would have looked like at that time. Big ferns, 100-foot tall, look like sequoias, big trees today, but they're ferns. Hardwood trees don't exist yet. And you're going to see finally land animals. Here's the very first amphibians, maybe reptiles, starting to evolve. And if you don't like bugs, do not go back in time to this time period, because this is the era of really big bugs. Giant dragonflies are 2 foot long, centipedes, millipedes that are 5 to 10 foot long. Lots of big, big bugs. They kind of ruled the roost. If you're an entomologist, great time. One of the things that these big bugs tell us, by the way, oxygen content was very different at this time. Everybody thinks of our atmosphere, 21% oxygen, as being pretty constant. And it has been for the past several hundred million years. But during this time period, oxygen content was 25 to 30%, not the 21% you're breathing right now. These coal forests pumped out a lot of oxygen. The end result is that big bugs could form, because they don't breathe like you and me. They breathe by diffusion. They don't have lungs. And so they actually have to diffuse through little spherical channels through their abdomens all the oxygen into their tissues. Well, in 21% oxygen, you can't diffuse that far. They would actually die of hypoxia, essentially. But if you have a 25 to 30% oxygen environment, you can get bigger bugs. And that's why they were so big back then. You can't have giant dragonflies now. They can't exist. They can't breathe. And that's backed up in multiple things. Just calculations on diffusion rates in insects versus isotope studies all show 25 to 30% oxygen during this time period. Again, the Earth has been very dynamic. And of course, all these coal forests die, they get buried, and you get coal. And all coal really is plant matter, all those giant fern trees crushed on top of each other, flattened, and sometimes, especially at the top of these layers, you can still see where they haven't been crushed too much, all the plant fibers mashed together. That's really all coal is. And coal actually does preserve fossils. Here's an amphibian skin. We actually got a skin fossil from someplace here in Ohio, the Diamond Coal Mine. And here's something, bony fish now exist. We know because we're finding fossils of them. Somebody bit the poor little guy's head off, but here's the tail. And it's a bony fish. They're finally now in the waters. The fish that we think of today that are everywhere finally exist in Ohio history. And at last, we get to the very, very last geologic period of both the Paleozoic as well as Ohio, and that's the Permian period, about 245, 290 million years ago. And by now, Gondwana has really merged with everything. Pangaea now is the continent. And we are actually north of the equator finally. Yay, going to where we are today. Unless you don't like winter, in which case, boo. Because I kind of like that whole southern tropical palm tree thing, but oh well. We're north of the equator, we're in Pangaea. This is what the world looks like in our neck of the neighborhood, and we are firmly landlocked. And we will remain landlocked pretty much for the rest of our history. As far as we know, Ohio never went back to the ocean, so to speak. Dry land, and this is what the world would have looked like then. All those things that have come ashore have diversified. You've got amphibians, reptiles, you've got insects, and you have this guy, Dimetrodon. Everybody, I think, who ever had a dinosaur set knows what Dimetrodon is, the big sailback animal. I don't know why they include them in dinosaur sets, because they're not dinosaurs. Dinosaurs are still another 50, 75 million years away. But they always put them in a dinosaur set. And by the way, Dimetrodon is a mammal ancestor, not a dinosaur ancestor. It was not even a reptile. This is the earliest, one of the earliest mammals, or proto-mammals. It's not a full mammal yet, but it's on its way. And so this is kind of the end of Ohio's geology, but it's also almost the end of the Earth, because something really profound happened at the end of the Permian. They call it the Great Dying. 95% of life went extinct on the Earth at the end of the Permian. And that's why the Paleozoic ends at the Permian. They don't know why. They still argue. A lot of things were happening in the world at the time. The Siberian traps were erupting. Essentially, all of Siberia covered in 50 to 100 foot of lava in massive volcanic eruptions. There was a stagnant ocean. There may have been asteroid strikes. A lot of things going on. Nobody really knows why, but 95% of life on Earth went extinct at that time. Very few made it through. But those that did went on to thrive in the Mesozoic. That included dinosaurs, proto-dinosaurs, and reptiles, later mammals in the Cenozoic. But this is the biggest mass extinction in Earth's history. And that's also where Ohio's history ends, which I think is kind of fitting. Or does it? Maybe I lied to you a little bit. We actually still do have some later geology in Ohio. Glaciers. That's really our most latest geology now. Probably responsible for taking away all that geology in between, but this is where all the glacier lobes went in Ohio. You can actually see terminal moraines, that's these little green things here, the big hills. If you're driving through Ohio going south, you'll go up over a hill, down, along some flat area for a while, up over a hill, down. You're actually going over these giant terminal moraines. What that is essentially the glacier is pushing forward and just pushing soil and gravel and sediment and ground up rock in front of it. And this was during the retreat, so they advanced to the furthest extent possible, then retreated, never to return. Then they'd pulse forward, put the next rain down, then pulse back further. And actually, they didn't just smoothly go back. They'd pulse forward, draw back, pulse forward, draw back, pulse forward, and this is the end result. And you can see all the way down here is where the glaciers went. The only place in Ohio that escaped the glaciers was the southeast corner of the state. And of course, that's the most mountainous too, because those glaciers didn't rub everything down to a flat, featureless landscape like it did everywhere else. This is our geology for the last 14,000 years. This last one that came through was the Wisconsin. It ended 14,000 years ago, and it's not the only one. For the past 3 million years, there's been dozens, maybe up to 50 glaciation cycles. It's been going on for a while. The one before the Wisconsin, the latest one, was the Illinoisan, and then there's a bunch of others that they kind of have fragmentary information on. The problem is glaciers tend to wipe out what came before. It's really hard to study. But this is kind of our latest geology. And if you were standing here back before 14,000 years ago, say 20,000 years ago, this is what Ohio would have looked like. But you better go up a mile, because we're under a mile-deep ice sheet. That's how big and thick the ice was here. It was not a place that was very hospitable to life, but once these glaciers withdrew, they left behind all of that glacial till. There's bogs from glacial kettle lakes. It's a big hunk of ice that is left behind as the glacier retreats. It takes a long time to melt, and that's what a kettle lake is. It's just a depression where that big hunk of ice used to be. And then forests, first grasslands started to grow, and then finally small forests, shrub forests, eventually bigger forests, sedges, trees, bogs, all sorts of stuff, and that brought a whole new fauna to Ohio. Mammoth, mastodon, giant ground sloth all lived in Ohio. Mammoths were more of a prairie animal. They tended to eat sedges and grasses. The mastodon is a forest animal. Yeah, they're both elephant relatives, but very different environments between these two. Grasslands, forest environment. And mastodons are much more common in Ohio, but there were mammoth here as well, especially soon after the glaciers retreated and it was all grasses. And we're finding remains of those guys today as well. Here's back in 1989, a golf course went to dig itself a new water hazard. Turns out they were on top of an old bog. And at the bottom, they found a mastodon skeleton. Not sure how old, but probably 10,000 years old, give or take. And here's his head, lower jaw, some ribs. We're still finding fossils from today in Ohio that are relatively new, not completely mineralized. These are still partially bone. They are not completely fossilized yet. On its way, but not yet. But this is the latest geologic history of Ohio. And it shows that geology is dynamic. Geology is continuing, even today, and will continue long after we're gone. Geology will be around, preserving everything, changing the landscape, and kind of recording what the area looked like back in the past. So now, hopefully when I say Ohio, you get something more like this in your head, rather than that boring road map. So thank you very much, and if anybody has any questions, I'd be happy to take them. Any questions? Yes?
You said that we don't find dinosaur bones in Ohio in the rock form before the dinosaurs lived. But does that mean that dinosaurs never lived in Ohio?
Oh, so the question is, even though we don't find dinosaur bones here, does that mean they never lived out? No, they actually did live here. It's just those sediments are gone. North America was a big dinosaur area. Lots and lots of dinosaurs actually lived here. Unfortunately, no geologic traces of them in Ohio. That was all taken away. Either the deposits never lasted, never were laid down, or my pet theory is the glaciers took them away. Darn those glaciers. But nevertheless, they were here, and they did live here, but we'll never know what was here because we have no evidence. Good question.
What caused the Dunklosaurus and sharks? They needed salt water, or?
Oh, so what environment did Dunklosaurus and?
What got rid of what?
Oh, so Dunklosaurus and Cladoslack, the sharks, were all salt water. We were obviously a sea. And what got rid of them is the Devonian extinction. Not sharks. Sharks are still around today. But placoderms actually did make it up through, I believe, the Permian, and then they were killed. But the Devonian extinction, another major extinction event, got rid of a good portion of the armored fish. And again, nobody quite knows what happened in the Devonian extinction. There's been 5 major extinctions on Earth. The Permian's been worse, and there's been other ones, the Devonian, the end of the Ordovician. Of course, everybody knows about Cretaceous. The dinosaurs went extinct. And some would argue we're in the 6th mass extinction right now. We are losing a lot of fauna very quickly. And I guarantee you, in 100 million years, future geologists are going to look at now and say, oh, extinction event. You know, we lost 60, 70, 80% of the life on Earth. Why? Well, we know why. But we are probably in the 6th mass extinction of Earth. Extinctions happen for a lot of different reasons. It's not always asteroids. It can be acidification of oceans. That's actually a big one for the Permian, where too much CO2 in the atmosphere. CO2 always seems to figure into a lot of these extinctions, by the way. It actually turns the water acidic. Shellfish can't form shells. Bones don't form. Hostile environment to marine organisms particularly. But that ripples up through the food chain. And some of them may be due to just stagnant water, lack of oxygen. That's another one that's been floated, especially for the Devonian extinction. But nobody really knows. Very controversial. Even the dinosaur extinction by the Cretaceous is not set in stone. Yes, the asteroid hit, very well established, but was it really the thing that killed them all? Or was there more going on? Because the Deccan traps were happening in India at the same time. Remember I mentioned the Siberian traps in the Permian? The Deccan traps were happening roughly the same time, and all of India was, again, covered pretty much in 1,500 foot of lava over multiple cycles, right at the end of the Cretaceous. lots of things are happening. And, you know, North America, South America are kind of getting together. Things are moving around. Extinctions are complicated things. And there's usually not one cause. It's a bunch of causes all combining to cause it. One thing alone probably wouldn't do it, but a bunch of things together would. And unfortunately, the evidence is sparse. They're still controversial. There's still controversy on the Cretaceous extinction. We're not sure exactly what happened. I definitely think the asteroid was not helpful, but there may have been other things going on as well that did not help either. Yes?
The Great Lakes are as a result of the ice ages?
So the question is, are the Great Lakes from the ice ages? Yes, they are. The Great Lakes are solely due to all of the ice ages. And so Lake Erie is the path that the glaciers came down. And it's actually a prehistoric valley. They followed the path of least resistance. And each glaciation period would come through and make it bigger and make it deeper. Here's an interesting fact. The Cuyahoga Valley today is actually a tiny version of what it used to be last time, or several glaciation cycles ago. Buried under the sediment is a massive thing that's 3 to 5 times wider and about double the depth of the current Cuyahoga Valley. And it's all glacial till that's filling it up. But glaciers have come through and scoured through multiple times. And all of the Great Lakes was formed by that scouring repeatedly. Glaciers coming and going, following old river valleys and paths of least resistance. Good question. Yeah.
A few miles north of here, you go to Menor Headlands.
Yep.
And you get the beach out there. All the sand, I assume that's ground up sandstone. But if you walk around, people are always out rock collecting out there. And there's all these pink rocks and all different kinds of things out there. Any idea where all that comes from?
So, yes, I do. So when you walk the landscape here, and it could be at the Menor Headlands, it could be in farmers' fields or streams, you often find, you mentioned pink rocks, that is Canadian Shield pink granite. It comes from hundreds of miles to our north and east. The glaciers brought it here. They're called glacial erratics. Those glaciers picked up rocks from hundreds and hundreds of miles away, dragged them down here, and when they left, they dropped them here, which is frustrating from a geology standpoint because those rocks do not belong here. There is no granite in Ohio unless you go really deep. But it's thanks to our friend the glaciers. And they've brought a lot of different rocks, not just granites. They've brought sandstones. They've brought basalt rocks here. All sorts of crazy stuff. One of our friends actually found a big piece of basalt that probably is a glacial erratic from Quebec, is what the thinking is. So there's lots of rocks, especially on the shoreline, because they're easy to find. The lake has done a nice job of sorting, sifting, and moving everything in. And yeah, you'll find rocks from all over North America concentrated here because of the glaciers. Yeah.
So the ice age that brought all that glacier formation, what causes that cooling in the first place?
So what causes the ice age? Couple of things. One, CO2 in the atmosphere. Very strong correlation between ice age pulses and CO2 in the atmosphere. Very strong. And that correlation doesn't go back just 3 million years. That correlation goes back hundreds of millions of years. That, again, looking at oxygen isotopes and things, they can tease out what CO2 levels were roughly. And it's a very strong correlation through all of geologic history of CO2 levels causing heat and cold. So that's one thing. But there's a little bit more complication with the latest series. Some of it has to do with the orbital period of the Earth. They've got all sorts of, there's like 3 or 4 different cycles all kind of superimposed on top of each other. And a lot has to do with the precession of the Earth, the tilt of the Earth. Right now we're at roughly 21 degrees tilt. That has not always been the case. And sometimes the tilt gets more or less, and that can cause cooling and heating. By the way, it's not distance to the sun. We are a slightly elliptical orbit like every planet. We are actually closest to the sun in the northern hemisphere's winter. So that's not a thing, It's the tilt of the Earth. And there's a 21,000 year precession cycle on top of several other 30, 35,000 year cycles. I think 160,000 year cycle. Little orbital mechanic things that all add up. And there's actually a pretty good correlation with those cycles and glaciation periods when you superimpose the effects of all those cycles on top of each other and what the Earth is doing, and then look at what the glaciers were doing. There's a fairly good correlation. So it's, again, not an easy answer. It has to do with atmospheric chemistry as well as orbital mechanics. It's both.
So as the climate change that we observe here, is that related to how all these other geologic and rotational changes happen to come together?
So current climate change, you mean? So current climate change, if you look at just the orbital mechanics, we should be cooling right now. We're going the other way. The atmospheric chemistry is greatly overriding. In fact, we are warmer now than we have been in 3 million years, which was the start of the glaciation periods. And it's doing this exponential, crazy, straight up. One of the problems is when you look at glaciation periods before, is that they tend to be, slow onset, slow offset, over hundreds of thousands of years, tens of thousands of years, even hundreds of years. We are doing in decades, in single years, what usually took hundreds of years to thousands of years to happen, or tens of thousands of years. It's a very abrupt spike. And that's probably bad. That is very unnatural. That doesn't occur anywhere else that they've ever seen. So it's definitely us, as much as people don't like to hear it. But unfortunately, it's mostly CO2. If it were orbital mechanics, we should be coming out of a interglacial period and going back to a cooling period. In fact, remember the late 70s? They said, glaciation's coming. We're going to go ice age again. That was based more on when they first discovered the orbital thing, and the orbital thing said it should be cooling. Well, no, we went the other way. We're getting hotter, and that's all due to atmospheric chemistry. Any other questions?
The 2/3 of the state of Ohio, fairly flat, except for the moraines. Then you got the 1/3 in the southeast, non-glaciated, or at least wise in the last glacier or whatever.
There we are.
That one.
Yep.
What are you going to see the differences in the soils and stuff like that in that regard? Closer bedrock, not closer bedrock?
Why did the glaciers go one place versus the other?
That, and what is the difference of the soils and the properties subterranean?
So it's not so much subterranean, but the glaciers coming to certain portions of the state, not others, affected, as you said, the flatness. Boy, that flatness is just wonderful up here, because that's where the glaciers were the thickest. And the reason this is much more mountainous in the southeastern part of the state is because the glaciers didn't get there. So a lot of the foothills of the Appalachians and all are still preserved. And that's actually what kept the glaciers out. They were tall enough probably. Glaciers always, just like water, take the path of least resistance. They'll go around. They're not going to go over unless they can really, they're really high. And so in the end result, they're coming down Lake Erie. They hit the end of Lake Erie, and they just kind of spread out. Meanwhile, you got to remember, right off the map here is the Appalachian Mountains running through Pennsylvania. And so the ice never really got to the Appalachian Mountains. In fact, the Appalachian Mountains kind of became a sanctuary for life. There were still forests and plants and trees that all took refuge in the mountains when the glaciation covered everything else. And so in a way, the Appalachians formed as an island of life in the middle of a glaciated landscape. That's why they didn't get there. The soils are different because you got to remember what the glaciers brought with them. Essentially glacial till. It's ground up rock, clay. That sand that Menor headlands is actually glacial. If you've ever been to the northern part of the lake, the north side of the lake, the Canadians have a lot more sand than we do. They had a lot. If you've ever been to Sleeping Bear Dunes in Michigan, Lake Michigan, that's all glaciated sand. That's ground up rock from the glaciers. And some places, a lot of sand was deposited. The southern shore of Ohio, or southern shore of Lake Erie, not so much. We only get a little bit of sand, just enough to make the headlands, Presque Isle at Erie. But if you go across the lake from Presque Isle, there's this massive peninsula called Long Point that just goes out, way out into Lake Erie. That's all glacial sand too. So the soils are going to be, for the areas where the glaciers went, mostly clays and things like that, then modified and turned into topsoil over the last 14,000 years. Whereas the mountain stuff, since there was never any ice there, have older soils, denser, more probably richer soils, simply because they didn't get glaciated. However, they're in mountains, so take your pick. So that's why you're going to find different soils in different places. It's just glaciers leave different things than where they didn't go. Yeah.
And how much salt is left? Are we going to run out of salt down there?
Are we going to run out of salt? Not in anybody's lifetime. So it's 2,000 foot down from us, and actually it extends in all directions. They have salt mines in Michigan, same stuff, same deposit. They have salt mines in Canada, same deposit. They have salt mines in the eastern part of the state. They have salt mines in Pennsylvania. Oswego has salt mines, all the same deposits. So no, we're not going to be running out anytime soon. This is not table salt, by the way. This is kind of road salt. This is not really good eating salt, but it's salt. It's more magnesium salt than it is sodium chloride salt. But nevertheless, it's a salt. But yeah, no, there's no danger. Oh, and there's no danger of draining Lake Erie into the mines. Lake Erie here is only 60 foot deep. The mines are 2,000 feet down. That's a lot of rock to get through. Nobody's going to accidentally break through and drain Lake Erie into the mines. So don't worry about that. Yeah, I know. It would be great cave diving. I understand completely, but yes.
Southeast Ohio, Pennsylvania, West Virginia is coal country.
Yep.
You can find a lot of coal there. It's also, I don't know if it's coincident or not, that's where the mountains are coming up. Is there coal in the rest of Ohio, or why is it only in that part of the state?
So why is the coal in that part of Ohio, and why is it elsewhere in Pennsylvania and surrounding West Virginia?
Lake County, or is it maybe down further?
So a lot of for the answer to the first question, of course it's in Ohio because we were pretty much at the perfect area for coal forests. We're on the coast. By the way, it's rich and as green as the Carboniferous was. That's the Pennsylvanian, Missouri, Mississippian, mostly Mississippian for us. The interior of Pangaea was a desert. And in fact, they had these horrible global dry spells, and then really wet periods, and then really big dry spells. Show up really well in the geologic record. So don't think of it as a rain planet, because that was only true on the coastlines, which we happen to be at. Also, West Virginia and Pennsylvania were pretty much in the same boat we were. They've since been uplifted with collisions with Africa and things like that. And so those coal deposits have been lifted up continuously as more collisions happen. And then the mountains get eroded away. One thing that's really cool is you have to remember the Appalachian Mountains, when Africa was colliding with us, looked like the Alps. They were huge. I mean, like the Himalayas maybe. I mean, absolutely mountainous, excuse the pun, mountainous range. It's all since been eroded away. You got to remember that's 300 million years ago. The Appalachian Mountains, all you're seeing is the roots of those mountains. What was there is all eroded and gone now. They're just stubs of mountains. But they used to be a magnificent range back in the day. And the coal that was buried under all that has now been exposed again. It's very close to the surface. So that's why coal is mined there, because it's very accessible. In fact, it can be gotten to from the surface, which is true in Ohio too. There's surface coal as well. You don't have to dig deep, which is more expensive.
I just want to make a comment. You were saying that we know that the tilt of the Earth on its axis is the reason for the season. So the northern hemisphere in winter, we're actually closer to the sun. So the question I had when I took a weather class is, why isn't the southern hemisphere really, really cold in the winter and really, really hot in the summer? And the answer is it's more water, much more water, which takes 5 times longer to heat up.
Yeah. So the observation that southern winters don't tend to be colder, well, first of all, you're not talking to anybody that has to winter over in Antarctica. Brutal. But nevertheless, you're right. So the oceans have actually been moderating our temperature rise. For the past 20 years, the oceans have been taking the brunt of the heating. Most of the heat's been going into the oceans. And of course, more ocean in the southern hemisphere means the southern hemisphere is going to stay warmer. The ocean's reaching its limits, saturation limits. In fact, one of the things that really terrifies me is the shutdown of the Atlantic conveyor system. So what is the Atlantic conveyor system, you ask? Good question. The Atlantic conveyor system is the Gulf Stream. That's a small part of it. But it's actually a worldwide circulation system that starts in the Pacific, goes all the way through the South Atlantic, up to Iceland, submerges from cooling water, and then there's a reverse current that goes back along the same way. It does two things. Essentially, it's a heat pump. It's bringing warm water up to the northern hemisphere. Look at the latitude of France, Paris, England, all these places in Europe, and compare them to North America. Quebec and Paris are almost the same. I mean, why is Europe so warm? The Gulf Stream, the Atlantic conveyor system. And there was, right about 14,500 years ago, a shutdown of the warming of the last end of the glaciation period, where for the next 500 years it crashed back into glaciation periods and then came back out. They've often debated why. Why did that happen? The Maunder minimum, I think it's called. And one of the speculations is that the warming northern hemisphere, Iceland or Greenland in particular, suddenly had a massive melt of water, fresh water, that dumped through into the North Atlantic and shut down the Atlantic conveyor system for about 500 years, plunging Europe back into an ice age, plunging North America back into an ice age for another 500 years when it had been warming. If continued warming happens and Greenland is melting really fast and a big pulse of fresh water hits the North Atlantic again, it could shut down the Atlantic conveyor system for hundreds of years, maybe for a long time, thousands of years, who knows? If that happens, Northern Europe is not going to be habitable. It's going to be a very different environment than what used to be. That's the type of changes that are actually true global climate changes. It's not that everybody's going to get warmer. Some places are going to get really cold as a result of it. It's on average going to be warmer. But if that warm tropical water isn't being brought up to the northern hemisphere with the Gulf Stream, bad things in Europe are going to happen. And that's happened, they think, in the past about 14,000, 15,000 years ago. So that's really what climate change is. It's abrupt changes in things that we've taken granted for a long time. And it may not be, we won't be taking it for granted if that happens. So those are the things that keep me up at night.
What about the fracking, the gas? How is that formed? We read about that in the newspaper.
Oh, so fracking?
Yeah, all that stuff.
So what fracking is essentially they're going after the shale deposits, which, they're organic. And there's gas in it, natural gas from, in fact, one of the problems around here is when shale degrades, it gets, natural gas because it's organic, but it also produces radon. It's slightly radioactive. And that's why radon in this area is a big problem. It's the Cleveland shale. It's actually creating radioactive gas that trickles up into people's basements. But of course, the natural gas is what the fracking is after. And what they do is they deep inject high pressure water, salts, and all sorts of nasty chemicals down there. And they essentially force the rock to crack, because shale is pretty brittle. And they force it all to they put it in one well, they inject the water and chemicals, and force cracking along an entire shale deposit. We're talking down thousands of feet. And then they have another wells around it that then get that escaping gas and collect it and pipe it to the surface. That's what fracking is. And it's quite controversial. I do wonder what we're doing down there. You've often heard of deep well injections causing earthquakes. I don't think we have to worry about that here. We get small earthquakes from buried faults. But from a biological standpoint, those chemicals are not really nice, and they have made it to the surface in other places, and they could come back. I mean, again, we always keep throwing things into the ocean and never expect to see them again. And then they come back to haunt us. And so all this deep well injection stuff kind of concerns me. Might be back to haunt us in 50 to 100 years. Who knows? I mean, and there have been cases in Pennsylvania, I think, where people's water wells have been poisoned from it. And that's, if a lot of people with water wells should be concerned in that sense. But that's what fracking is.
Read about the North Atlantic fisheries.
Yeah.
How they're changing. And the slowing of the speed of the Gulf Stream and the widening of it, which is causing the coastal areas to become warmer.
Yep.
Which is also increasing the depth of the height of the tides because of the slowing of the Gulf Stream. So you shoot water one direction and it pulls water in with it.
Brutally effect, essentially.
Correct. And with it slowing, that's why they're saying certain areas of New England now have sea level rise greater than other spots due to the broadening of the Gulf Stream.
So it could very well be. I've not heard anything about that. But tides are actually really hard to predict because it's a combination of gravitational tidal effects with bottom bathymetry, focusing and unfocusing. So like Bay of Fundy gets really high tides because that long, narrow valley essentially that creates. And then, yes, water dynamics like the Gulf Stream, which is a very fast-moving body of water, could have effects like that too. I hadn't heard of that, but I wouldn't be surprised. So the other thing too is you mentioned the warming, and that is definitely making fish that are tropical going further north. They're now seeing tropical fish from Florida up at Cape Cod because, well, warm water. And that's a little surprising. Who expected to see them up there? But there they are. And you're seeing it here on land too with warming air. Birds are going north further, that sort of thing. So we're seeing all sorts of changes. It happens in the water. People don't notice it as much. Divers do, but fishermen do. But yeah, I mean, there's a lot of changes if you warm the water as far as movement of both the wildlife as well as currents, possibly tides. I wouldn't be surprised because they're very hard to predict, very hard to model. But yeah, those are all changes that could happen.
Thank you so much.
All right, thank you.